So this talk was originally supposed to be by Becky, but happy to say Becky had a baby last weekend. So cool. Instead you get me.
Congratulations to her. All right, it's 4:30. So if you are ready, Oliver, the stage is yours.
Okay, thank you, Nicola. Okay, so this is joint work with Becky Petrios, who can't be here today. Yeah, so we're studying a problem in post-set dynamics. So I'm going to take a partially ordered set, and I want to look at the collection of all of the order ideals. So these are sets that are closed downward. You take some, if you have some element in your order ideal, then everything below it is in your order ideal. And so I have this collection of all the order ideals in my post-set. And I want to study an invertible operator on the set of these order ideals. And the way it works is you take your order ideal, and you look at the smallest elements, the minimal elements that aren't inside it. And you take those minimal elements of the complement and you let them generate an order ideal. You just close them downwards and you get a new order ideal. Okay, so this is something you can do. It takes an order ideal, gives you a new one. If you think about it a little bit, it's going to be invertible. And so you get some permutation of the set of order ideals. It's an invertible map from the set to itself. And what we want to understand is what is the cycle type of this permutation? So if you take a sort of generic poset and you look at this associated permutation, you can't really say much about it. The permutation is kind of a disaster. We know nothing. But you know, at FPSAC, we don't really like to study generic posets. We like to study really nice posets. And if you have your own favorite really nice poset, probably row motion is actually quite nice in that context. There's probably a lot of structure in that permutation. And this morning, I'm telling you that your favorite poset is the product of three chains. So this is just triples of positive integers under component-wise comparison with A, B, and C bounding the three components. Okay, so we're going to study this poset. We're going to study row motion on this particular nice poset. So what is the history here? What is the motivation? Well, basically the first source of row motion is this 1974 paper of Brouwer and Shriver, where they prove a couple of things, not for any really obvious reason, but it's a very cute little thing. And then nothing really happens for about 20 years. And then there's this other paper that shows up with Peter Cameron and Dima van der Vlas. They prove a few more things. Still not entirely clear why they're doing it. And then nothing happens for like another 15 years until about 10 years ago. Penyushev writes a paper about row motion in the context of posetsets coming from root systems. And suddenly people start to get excited about row motion and a lot of work starts happening. And you know, at this point, it's not really clear why we're doing anything yet. It's sort of, it's almost like a recreational problem, but it's no longer a recreational problem. Suddenly, you know, recent developments connects row motion to sort of other rich parts of algebra and combinatorics. And this is here's a very selective list of connections, very even more selective list of references, but you can see there's things going on these days. And the last one's in red because that's the perspective that we're going to take this morning or this afternoon or whatever time zone you happen to be in. It's my morning. Okay, so back in 1974, Brouwer and Shriver were really studying the product of two chains. And so I snuck that into the same framework by just setting C equal to 1. So it's kind of not there. And what they observe is that even though you have this large set of order ideals, every orbit is actually quite small. I have this set is growing. This is like A plus B choose A. Right, it grows quite quickly in A and B, but the largest orbit sizes, they're only growing like A plus B. So this is a lot of surprising structure. Right? The orbits are much smaller than you would expect. And that was what we knew at the time, but now we know actually much more. Actually, if you take the Q enumeration for order ideals according to cardinality, and you stick in roots of unity, you'll get some numbers that tell you the full orbit structure. It's going to tell you exactly how many cycles of every size, all hidden inside there. All right, so that was 1974. And then we wait 20 years for Cameron and van der Vlas to think about the case C equals 2. And what they observe is basically the same theorem. When we went from c equals 1 to c equals 2, the orbits just got bigger by 1. Not so strange. Okay, and that was what we knew back then, but now we know, in fact, there's a similar kind of cyclic sieving result. You take this Q enumeration by cardinality, and you evaluate roots of unity, and you can control the entire cycle structure. It's all hidden inside. Okay, so now we go forward another couple of decades to the case c equals 3, and suddenly we don't really know what's going on. Conjecture is that when we go from 2 to 3, again, the order of the action goes up by 1 once again, but this is very open. We don't know how to do this. And maybe one way of seeing that it's hard is that you can try to write down the analogous cyclic sieving result. You can take a Q enumeration by cardinality and put in roots of unity, and it's not going to give you what you want. Right? Something much more subtle is going on in the case. And you go to 3, and then you go to 4 or above. Past that, it's all starts to fall apart. So you would guess maybe every time c gets bigger by 1, you would guess that the order of the action would also get bigger by 1 by analogy. You might expect it to be this in general, but it's not that. It's generally much larger, and we don't know what it is, and we don't even have bounds on how big it could be. Because they're just some examples. If I take A, B, and C equal to 4, then this sort of like naive guess you would have made would have said 11. All the orbits should have had size 11, but you can just compute them all, and some of them have size 11, but you know there's some also that have size 33, 3 times 11. And if I take A still 4, but I make B and C get up to 11, then the naive guess would be to have orbits of size 25. But I know of an orbit whose size is 309 times 25, and maybe there's bigger ones. That was just the biggest one I could find. So, we don't understand what the order of this action is. We get some very large and surprising orbits, and it's hard to even know how to guess anything like a cyclic sieving when you have no idea what the order of the action is. No idea what roots of unity to plug into what. Okay, so this conjecture of Cameron van der Vlas, going back to this 1995 paper, was some sort of attempt to salvage the situation, right? So we don't know what the order of the action is. We can't put bounds on it. And yet they're going to tell you something very restrictive about what the orbit sizes can be. They say, well, suppose this sort of naive guess for what the orbit size would be is a prime number. Well, then that's not actually the order of the action. My orbits won't be that size, but they're going to be multiples of that size. So they're not going to be sort of any possible large number. They could be very large, but they're going to be some kind of controlled way of being large. They're going to be multiples of the thing that you originally hoped for. This is not like the most obvious kind of control to get over orbit structure, but it's a thing that you can guess. So their evidence for this conjecture was a lot of computational evidence. They computed a lot of things. And they could also prove this sort of the regime where C is very large relative to A and B. If C is sufficiently big, then it's okay. So they made this conjecture, and it seemed like very strange. And this condition here in particular, it seems like very hard to figure out what to do with. It's just a weird sort of thing. Okay, so that got made, and then like no one paid attention for a while because no one really followed up on this paper until Panyusha reminded people about this topic. Finally, a few years ago, with Kevin Dilks and Jessica Stryker, we were able to like slightly improve this large C regime where it is definitely holding. But the main result of this work and of this paper with Becky is we can actually prove the conjecture now. And the key to making the conjecture go through is figuring out how to state it in more generality, how to state it without the bizarre primality condition here. And the right thing to say is that, well, look at your order ideal, look at the orbit, look at how big that orbit is. It could be huge. I have no idea how big it is, but what it can definitely never, ever be is relatively prime to the thing I naively guessed it would be. So why does this prove the conjecture? Well, if the naive guess was a prime number and I'm not allowed to be relatively prime to it, then I must be a multiple of it. Okay, and that's the conjecture you wanted to prove. Okay, but this is the more general statement. If it's not prime, then I can, of course, get not just multiples, but also divisors and multiples of non-trivial divisors and things. All sorts of other numbers can show up, but there's still many numbers that can't show up. We got a fair amount of control over what kinds of cycle types are plausible. Okay. How am I doing? All right. So the trick for making this go is to use combinatorics that we steal out of the K-theoretic Schubert calculus literature. And this won't a priori look like we're doing anything the same, but it is secretly going to be the same. So sort of a classical thing you do in Schubert calculus is you take standard tableau of some skew shape, and you have some rectification action on standard tableau of skew shape, sort of a jeu de taquin, and you use this to compute the Schubert calculus of Grassmannians, the cohomology of a Grassmannian. Well, what we're going to do here is something slightly more general. I'm going to look at increasing tableau. So these are like standard tableau, except I'm allowed to repeat my numbers, but they're still strictly increasing both in rows and in columns. So they're sort of more symmetric than a semi-standard version of things. Right? There's no difference between the rows and the columns. I have things like this, and associated to them, there's going to be this K-theoretic notion of jeu de taquin. I won't tell you exactly how it works, but you can probably work it out what it has to be, because it's sort of the only thing you can do to preserve at every stage that you're strictly increasing in both rows and columns. I want to generalize the thing that you would do on standard tableau. I want to extend that, and I want to, at every step, preserve the class of objects I live inside. There's sort of only one way to guess, and in fact, the guess works. There's quite a bit of work to show that the guess works. Okay, when you do this, you're computing the analogous Schubert calculus problems, but in K-theory rather than cohomology. Okay, so ordinary jeu de taquin on standard tableau, you can use this, Schutzenberger, use this to create a promotion operator on tableau. And we're going to use this K-theoretic jeu de taquin on these increasing tableau to get a K-theoretic promotion operator on things. So it works exactly the same way, except with the letter K added. So I take my tableau and I throw away the number 1. And then I'm going to make all the numbers 1 smaller, like this. And then if this was a standard tableau, I would rectify it. I would just apply JDT into this corner and get some stuff. But now it's an increasing tableau, so I'm going to do K rectification. Well, what does this mean? I'm going to start sliding things into the corner. First, the 1 is going to slide into the corner. This is just like the standard story. And now I feel a little worried. I have these 2 3s competing to slide into this box. But you see, if this 3 slid up, then I wouldn't have an increasing row anymore. My row would be weakly increasing. And if this 3 slid over, then my column would no longer be strictly increasing. And so there's kind of only one thing I could possibly do, which is to move both of them at once. Now they don't interfere with each other, and just leave 2 holes. I can just do that. I get these 2 holes. Okay, and now I'm not sure what to do with the 4. It sort of has 2 places it wants to go. And by symmetry, there's no obvious way to choose between them. So we just do both at once before it goes in both places, splits up like this. Okay, so you can formalize this in some way. But then I get to here, and now there's no more slides I can do. It's a straight shape. And I will take the maximum value of the alphabet I'm thinking about and stick it in the remaining box. So put in the 5. Okay, so this is a new tableau from the one I started with. This is the K promotion. Right? This is generalizing the notion of promotion on standard tableau. I get this thing. Okay, so why are we doing this? Why are we doing this thing that looks like it has nothing to do with the topic of the talk? Well, what we learned a few years ago is that even though it superficially looks very different, this is secretly the same thing as row motion on plane partitions. There's an equivariant map you can write down between these two sets that takes the row motion operator here and carries it to the k promotion operator over here, which I'm writing with the same letter because they're sort of secretly the same thing if you set this bijection up correctly. Okay. So this turns out to be very useful, mostly in the form you have a problem you don't understand about plane partitions. If you take your problem you don't understand about plane partitions, it might be because it's secretly a problem about increasing tableau, and you were confused and you thought it was about plane partitions. And if you translate it into the world of increasing tableau, there's extra tools you have available to you. There's extra structure that becomes apparent, and often things become easier. So this is going to be an example of that, where this Cameron-van der Plas conjecture, which seemed sort of like a baffling statement about plane partitions, becomes much nicer in the language of increasing tableau. So we had already, used this idea to like get a little more evidence for the conjecture, but now we can push it all the way through. We know enough about tableau. Right, one thing is that on the tableau side, the Schubert calculus people, right, they've developed all this combinatorial technology for you because they wanted to compute some geometry, and so they built all these tools for how to understand k-theoretic tableau. Okay, so the fact we need sort of one key fact about promotion on increasing tableau. So if I take a standard tableau and it has numbers 1 through q inside my standard tableau, and my tableau is a rectangular shape, then it's a well-known fact that when you repeat promotion q times, you always get back the tableau that you started with. Well, that's not true for increasing tableau. The orbits are going to be bigger than that. So for example, if I take this tableau, this increasing tableau using the alphabet 1 through 11, and I do promotion 11 times, hopefully you'll believe me that what I get is this tableau over here. And this tableau is not the one I started with. It's almost the one I started with, but something went wrong in these two boxes. They shrank a little bit. And if I do it 11 more times, I'm going to get something else. If I do it 11 more times after that, I'll eventually get back to where I started. So actually taking 33 times to get around. Okay, so the key fact that we need, though, is that suppose I take an increasing tableau and I apply promotion alphabet size many times, q times, well, then I don't get back the original tableau. But what I do get back is something that looks the same around the boundary, looks the same in these boxes around the outside. It might look weird in the middle, something might go wrong, but it's always happening on this region on the inside. Okay. On the outside, everything's okay. And this fact is basically the key thing you need to make Cameron-van der Plas work. So the translation of Cameron-van der Plas into the language of increasing tableau is look at your increasing tableau of this rectangular shape and look at its k promotion orbit. Suppose it has size k. Well, then k is not allowed to be relatively prime to the alphabet size, with the only exception being that if the alphabet is small enough, then there's a unique tableau that exists with that alphabet. And since there's a unique tableau, it has to be fixed by the action. So there's one very special sort of degenerate case that shows up. Okay, so I think I have time to actually prove this theorem at you. So the trick is like this. So let me look at my orbit. So here's T, and I'm going to look at my orbit. All right, so here's my orbit of all these things. And what I know is, I'm going to go by contrapositive. Let me assume that my orbit size is relatively prime to the alphabet size. So here I've got 5 things in my orbit. my alphabet's going to be, let's say it's 2. That's obviously not a real example. Okay, well, what I've learned from that frame theorem is that if I apply promotion Q times, then I don't change the frame of the tableau. I don't change the entries around the outside. So I go from here to here and I have the same frame. And then I go from here to here and I have the same frame. And then I go from here to here and I have the same frame. And then I go from here to here and I have the same frame. And then I go from here to here and I have the same frame. In fact, because of this coprimality condition, in fact, everything in this orbit has the same frame. But that's exactly how we're using this fact. Well, if everything in the orbit has the same frame, then in particular, T and its promotion have the same frame. And that's just really hard to pull off. That just basically can't happen. Right? So then you have to go back and study sort of carefully, look at the definition of K promotion and think about what it would do to a tableau to have the boundary be exactly the same, have it not change at all. And it turns out the only way that could possibly happen is if your tableau has such a small alphabet that there's a unique filling. Right? If I'm looking at the tableau that looks like, for example, this, the one where every number is as small as possible, there's only one way to fill it. And so of course, like when you apply promotion, nothing happens. That's the only way that this can go around. Okay, so we get this statement and now we just convert back, right? We just translate this back into the language of plane partitions. And the sort of degenerate case, this one where there's only one tableau, this turns out to be plane partitions of height 0, which are not normally like the kind of plane partitions one thinks about, right? There's a unique one and it's kind of the empty set in some way. Okay, so there's that thing, and so we ignore that one. And then for everything else, we just translate this over. So what it's telling us is the theorem we had before, right? For our sort of generalization, the Cameron-van der Waals conjecture. But in particular, if you take your expected orbit size to be a prime number, as they did, then you see that every orbit of row motion in plane partitions in this box is going to be a multiple of that expected thing. Okay, so this proves this conjecture, but it doesn't exactly resolve all the questions one might have about the orbit structure of this thing, about what permutation we're looking at here. For example, we have still no idea what multiples show up, right? We know that every orbit is going to be a multiple of the naive guess, but we don't know which multiples there are. And in particular, we don't have any bound on how big they could be, right? In theory, they could be, well, the only bound I know is I can tell you how many plane partitions there are total, right? The McMahon formula for counting plane partitions. The orbits can't be bigger than the whole set, but that's about all we can say. So they could be in theory like extremely large, and we have almost no control over that. Even if you knew which multiples showed up, they don't show up with the same frequency. For example, you'll find that there are some orbits that are twice as big as you originally guessed, but there's going to be even more orbits that are 3 times as big as what you originally guessed. And I have no idea why that happens, but just experimentally, you see it a lot. In general, you're getting odd multiples of the thing you started expecting instead of even, you also get even multiples, but you get more odd multiples. I don't know why. Okay, and there's some missing geometry over here. So in the case where you think about a standard tableau, instead of increasing tableau, there's ways of interpreting this in terms of kind of monodromy actions over Grassmannians. And it's not clear how to lift that story into this increasing tableau plane partition setting. The obvious guesses for geometry are not the right thing, but there's this is some kind of hint of some sort of interesting geometric story going on over there. And if we could understand that, hopefully that would also tell us something about missing combinatorics and vice versa. Okay, so here is a picture of a plane partition, and thank you very much.
Thank you very much. That was a very nice talk. Questions?
Oliver, I have a question. question for you. So, because you're not getting cyclic sieving for general ABC, it's probably too much to ask for homomesses. But there's this new notion of homometry where you can have it even when the orbit lengths have, are relatively prime to each other. Has anybody looked at
Yeah, it
homometry?
doesn't work. It doesn't work.
It doesn't work. Okay.
But there is in fact some homomesy you can do.
Uh-huh.
There is homomesy. The trick is to ignore the middle of the tableau and only think about the frame.
Gotcha. Yeah,
If
that
the
makes
middle of
sense.
the tableau is where weird stuff happens, if you just restrict to thinking about the frames, then you can find some homomesies. I don't know what to do with them if they exist.
Great. Okay, thanks.
So there is a question by Joseph in the chat.
Oh, I wasn't watching the chat.
Not much happened except congratulations. And a question now.
Oh, have I checked the obvious extensions for products of four chains? Yes, it's a disaster. Like even in the case A plus B plus A, B, C, and D all equal 2, it's very bad. I don't know what's happening. There's something very special about the three-dimensional case. I mean, I can sort of explain why the three-dimensional case is special. It's because the three-dimensional case is really talking about these two-dimensional increasing tableau, and these increasing tableau of rectangular shape. This rectangular shape is related to Grassmannians, and there's some secret geometry that's making it all run in the background. So the extension of this that works is to change out this rectangular poset that we're looking at here for a poset, governing some other kind of minuscule Schubert variety, minuscule Zag variety. The four-dimensional thing, the product of four chains, that corresponds to like a three-dimensional increasing tableau. There's no associated geometry and everything falls apart.
Okay, thank you. We still have time for one more question maybe before the break. Oh, there it is. I know, it's just a comment from Bruce. Questions, anyone? All right, then let's thank the speaker again.